Now, some of the nitty-gritty technical details of doing these tests correctly and getting those powers correctly come down to how you measure things like a high fundamental frequency. So core to the technology of HBM is what we call a cycle detect. So we use a cycle detect algorithm to calculate power, and I'll just briefly explain that. So in the red trace, we have phase A current. This is the AC current coming out of the inverter. This is making the motor spin. The higher the frequency, the higher the speed of rotation. So since we're doing calculations in the hardware, we have a digital signal processor residing on the card. We filter this phase A current as it's coming into the card. We have some input variables, and we're able to find zero crossings. We take 2 successive zero crossings, and we call this our cycle time. From our cycle time, we average all those points up to 2 megasamples per second in between those zero crossings, and we either run an RMS or an average calculation based on what we're looking for. Each one of these half-cycle measurements is an 18-bit measurement, or half-cycle calculations is an 18-bit measurement, and it's very accurate in a dynamic scenario. So as frequency is changing, the cycle detector is tracking that frequency and giving us calculations on that half-cycle basis. So we can really start to have an accurate power in a dynamic setting. Now, some of you might be looking at dynamics and find this very exciting. Others might be doing steady state testing. If you're doing steady state testing and looking for an efficiency, each half cycle is an 18-bit measurement. And if you start averaging these 18-bit measurements together, you get a very, very high resolution measurement. So for steady state signals, even if your frequency is changing a little bit, which we'll touch on in a moment, you're getting a very high resolution measurement. It's cool stuff, and it allows us to test one very quickly. In just a matter of cycles, you can have a very, very high resolution measurement, or dynamically. If you want to increase frequency, increase load, you're going to be able to follow that and understand that power as it's changing dynamically. An example of dynamic testing with cycle detect, this is a machine startup where we have currents in red, voltages in blue. These are PWM voltages, and then again our power, reactive power, and apparent power in black, pink, and orange. And we can see that as that machine starts up, we have a small, slow frequency. The machine frequency increases, and that cycle detect tracks it right along. And we have all of this recorded, so we know and we have confidence that these power values are correct. Everything's recorded. You can always reference back. The system is auditable. So as that frequency is increasing, that power level we can see increasing, and we can track that in dynamic scenarios. We can find overshoots in power, like we see where my red dot here. Just a lot of good information for engineers to make decisions on how my machine actually operates in the field, how my machine operates in transients. And this also allows you to optimize your efficiency during transients. Again, it all comes down to how far can my aircraft fly. So cycle detect allows us to make these types of measurements where some other systems may not be able to do this. High fundamental frequencies. So many tools have incredible accuracies spec'd at 50 to 60 hertz. Now, many systems do not operate at 50 to 60 hertz, and if they do, it's not for very long. Some of these aircraft systems are going to a kilohertz fundamental, 2 kilohertz fundamental, and talking about going even higher. And if you look at the accuracies on other instruments in the market, they actually go down at high fundamental frequencies, which is really troublesome if you want high accuracy at those high speeds. So what I have on the screen is, again, another screenshot of some of our data. And we have a fundamental frequency in red with the cycle detect tracking it. In the middle, we can see that this is a 350 hertz frequency, well above 50 hertz or 60 hertz. And we can see that that frequency is even moving around a little bit. You know, if we look at a range between 340 hertz and 360 hertz, this is probably a plus or minus 5 hertz move. But if we average our cycles over a rotation of a machine or over a cycle of frequency change, we can get a very stable output in the steady state, even at this very high fundamental frequency. And if we go to one of our calibration sheets and we look at the measurement uncertainty and the deviation from a known value in our measurements, we can see that for For our power measurements, with frequencies of 50 hertz, we have a 0.01% deviation. Frequency of 500 hertz, we have a 0.01% deviation. Frequency of 5 kilohertz, we have a 0.03% deviation. These are very, very good values, and this is a measured calibration sheet from one of our units. So these are real values that we can expect to get. And when we go to this high fundamental frequencies, you really want to trust your measurement tool and know that it's going to perform at the operating points that you're going to operate at. Electric aircraft's a new world. We have to start looking at things differently, and high fundamental frequency is one of them.